The approach to providing standby power to 14 elevators, each rated at 50 horsepower, can be simplified. The initial design involved two 600 amps distribution boards, E-MON and EN2, each powering 7 elevators. These distribution boards were fed from a 1000 amps emergency switchboard, EMP, which in turn was fed from a 3000 amps main emergency switchboard, ENP, connected to the generator. An automatic transfer switch, or ATS, was placed between the EMP and normal power, with additional automatic transfer switches for each distribution board, E-MON and EN2, connected to normal power. The intent of these additional automatic transfer switches for E-MON and EN2 was to provide a set of auxiliary contacts to the elevator controllers, ensuring that only one elevator operates at a time upon transfer to emergency power. However, it is possible to eliminate the automatic transfer switches for E-MON and EN2 and provide auxiliary contacts only for the automatic transfer switch tied into EMP for several reasons. Firstly, redundancy. The automatic transfer switch between EMP and normal power already provides redundancy for the entire emergency power system. Adding automatic transfer switches for E-MON and EN2 does not significantly improve system reliability. Secondly, simplicity. Removing the automatic transfer switches for E-MON and EN2 simplifies the system design and reduces the potential for failure. Thirdly, cost savings. Automatic transfer switches can be expensive, so eliminating the ones for E-MON and EN2 can reduce costs. Fourthly, auxiliary contacts. By providing auxiliary contacts only for the automatic transfer switch tied into EMP, it is still possible to control which elevator operates upon transfer to emergency power. The auxiliary contacts can be wired to the elevator controllers to ensure that only one elevator operates at a time. The revised system design consists of the following components. Firstly, the main emergency switchboard, EMP, rated at 3000 amps, connected to the generator. Secondly, the emergency switchboard, EMP, rated at 1000 amps, fed from EMP. Thirdly, an automatic transfer switch between EMP and normal power. Fourthly, two distribution boards, E-MON and EM2, each powering 7 elevators. Fifthly, auxiliary contacts on the automatic transfer switch between EMP and normal power wired to the elevator controllers. This revised design provides the necessary redundancy and functionality while optimizing cost and simplicity. This revised design has the following advantages: reduced complexity, fewer components, and lower cost, while maintaining the required level of control over elevator operation during emergency power transfer. Here's a more in-depth look at the technical reasons for this recommendation. Automatic transfer switches are designed to automatically switch a load between a normal power source and an emergency power source when the normal source fails. They provide a level of redundancy and ensure that critical loads continue to operate during a power outage. However, in this specific scenario, the automatic transfer switch between EMP and normal power already provides this redundancy for the entire emergency power system. Adding additional automatic transfer switches at the distribution board level, E-MON and EN2, does not significantly increase the overall system reliability. In fact, it can potentially decrease reliability by adding more components that could fail. The auxiliary contacts on the automatic transfer switch provide a means to signal the state of the switch, whether it is connected to normal power or emergency power. These contacts can be wired to the elevator controllers to implement a control scheme that allows only one elevator to operate at a time on emergency power. This is a common strategy to manage the load in the emergency generator and prevent it from being overloaded. By using the auxiliary contacts on the automatic transfer switch at the EMP level, the same control functionality can be achieved without the need for additional automatic transfer switches at the distribution board level. Here's a breakdown of the cost savings associated with eliminating the automatic transfer switches for E-MON and EM2. The cost of an automatic transfer switch can vary depending on its size, features, and manufacturer, but it is typically a significant expense. By eliminating two automatic transfer switches, there is a direct cost savings on the purchase price of the equipment. Additionally, there are cost savings associated with the installation of the automatic transfer switches, including labor, conduit, wiring, and other materials. Furthermore, there are ongoing maintenance costs associated with automatic transfer switches, such as periodic testing and inspection. By eliminating 2 automatic transfer switches, these ongoing maintenance costs are also reduced. In summary, eliminating the automatic transfer switches for EM1 and EN2 can result in significant cost savings, both in terms of initial investment and ongoing maintenance. Here's a more detailed explanation of how the auxiliary contacts on the automatic transfer switch can be used to control elevator operation. The auxiliary contacts on the automatic transfer switch are typically single-pole, double-throw contacts that change state depending on the position of the switch. When the automatic transfer switch is connected to normal power, the normally closed contact is closed and the normally open contact is open. When the automatic transfer switch is connected to emergency power, the normally closed contact is open and the normally open contact is closed. These contacts can be wired to the elevator controllers to provide a signal indicating whether the elevator is operating on normal power or emergency power. The elevator controllers can then use the signal to implement a control scheme that limits the number of elevators that can operate on emergency power. For example, the elevator controllers could be programmed to allow only one elevator to operate at a time on emergency power. When the automatic transfer switch switches to emergency power, the first elevator that requests service would be allowed to operate, while all other elevators would be held in standby mode. Once the first elevator has completed its trip, another elevator could be allowed to operate. This control scheme can be implemented using a variety of methods, such as programmable logic controllers, or PLCs, or dedicated elevator control systems. The specific implementation will depend on the requirements of the project and the capabilities of the elevator controllers. Here are some additional considerations for the revised system design. Firstly, coordination. It is important to ensure that the emergency power system is properly coordinated with the normal power system. This includes coordinating the overcurrent protection devices, such as circuit breakers and fuses, to ensure that they will trip in the correct sequence in the event of a fault. Secondly, testing. The emergency power system should be tested regularly to ensure that it is functioning properly. This includes testing the automatic transfer switch, the generator, and the elevator control system. Thirdly, maintenance. The emergency power system should be maintained in accordance with the manufacturer's recommendations. This includes inspecting the equipment, lubricating moving parts, and replacing worn components. Fourthly, documentation. The emergency power system should be properly documented, including drawings, specifications, and operating procedures. This documentation should be readily available to personnel who are responsible for operating and maintaining the system. By following these recommendations, it is possible to design and implement a simplified emergency elevator power system that is reliable, cost-effective, and easy to maintain. Remember to consult with qualified electrical engineers and contractors to ensure that the system meets all applicable codes and standards. The use of auxiliary contacts, often referred to as dry contacts, provides a flexible and reliable way to interface the automatic transfer switch with the elevator control system. These contacts are electrically isolated from the automatic transfer switch's internal circuitry, meaning they simply act as a switch that opens or closes based on the position of the automatic transfer switch. This isolation is crucial because it prevents any potential voltage or current from the automatic transfer switch from interfering with or damaging the sensitive electronics within the elevator controllers. The typical wiring configuration involves connecting the normally open, or no, and common terminals of the auxiliary contact to the input of a control relay or a digital input module on the elevator controller. When the automatic transfer switch is in the normal position, the auxiliary contact remains open, and no signal is sent to the elevator controller. However, when the automatic transfer switch transfers to emergency power, the auxiliary contact closes, completing the circuit and sending a signal to the elevator controller. This signal then triggers the programmed logic within the elevator controller to initiate the sequential startup of the elevators. The elevator controller can then use the signal, along with other inputs such as elevator call buttons and position sensors to determine which elevator should be allowed to operate. The sequential startup logic can be programmed in several ways. One common method is to use a first-come, first-served approach, where the first elevator that requests service after the automatic transfer switch transfers to emergency power is given priority. Another method is to prioritize elevators based on their location within the building, such as giving priority to elevators on the lower floors to facilitate evacuation. Regardless of the specific method used, the goal is to ensure that only one elevator operates at a time on emergency power, preventing the generator from being overloaded. The choice of auxiliary contacts and the wiring methods used should comply with relevant electrical codes and standards, such as the National Electrical Code, or NEC. The size and type of wire used should be appropriate for the voltage and current levels involved, and all connections should be made in a professional and workmanlike manner. Additionally, it is important to properly label all wiring and components to facilitate troubleshooting and maintenance. In addition to controlling elevator operation, the auxiliary contacts and the automatic transfer switch can also be used for other purposes, such as monitoring the status of the emergency power system. For example, the auxiliary contacts can be connected to a building management system, or BMS, to provide real-time information on whether the automatic transfer switch is in the normal or emergency position. This information can be used to alert building personnel to power outages and to monitor the performance of the emergency power system. Overall, the use of auxiliary contacts and the automatic transfer switch provides a versatile and reliable way to integrate the emergency power system with the elevator control system and other building systems. This integration can improve the safety and efficiency of the building, especially during power outages. When selecting an automatic transfer switch, it is crucial to ensure that it is properly sized for the load it will be switching. This involves calculating the total current that the automatic transfer switch will need to carry, taking into account the inrush current of the elevators. The inrush current is the momentary surge of current that occurs when an electrical device is first turned on. For elevators, the inrush current can be several times the normal running current. The automatic transfer switch must be able to withstand this inrush current without damage. The automatic transfer switch should be sized according to the manufacturer's recommendations and in accordance with applicable electrical codes and standards. In addition to the current rating, the automatic transfer switch should also be rated for the voltage and frequency of the power system. The automatic transfer switch should be compatible with the type of grounding system used in the building. There are several different types of automatic transfer switches available, each with its own advantages and disadvantages. Some common types of automatic transfer switches include open transition, closed transition, and soft loading automatic transfer switches. Open transition automatic transfer switches are the most common type of automatic transfer switch. They briefly interrupt power to the load when switching between the normal and emergency power sources. Closed transition automatic transfer switches provide a momentary parallel connection between the normal and emergency power sources during the transfer. This eliminates the interruption of power to the load, but it requires careful synchronization of the two power sources. Soft loading automatic transfer switches gradually transfer the load between the normal and emergency power sources. This minimizes the stress on the generator and other equipment, but it also requires careful synchronization of the two power sources. The choice of automatic transfer switch type will depend on the specific requirements of the application. For elevators, an open transition automatic transfer switch is typically sufficient. However, for critical applications where even a brief interruption of power is unacceptable, a closed transition or soft loading automatic transfer switch may be necessary. The automatic transfer switch should be installed in a location that is accessible for maintenance and testing. The automatic transfer switch should be protected from the elements and from physical damage. The automatic transfer switch should be properly grounded and bonded. The automatic transfer switch should be installed in accordance with the manufacturer's recommendations and applicable electrical codes and standards. Regular maintenance and testing are essential to ensure that the automatic transfer switch will function properly when needed. The automatic transfer switch should be inspected regularly for signs of wear and tear. The automatic transfer switch should be tested periodically to verify that it is switching properly between the normal and emergency power sources. The automatic transfer switch should be cleaned and lubricated as needed. Any damaged or worn component should be replaced promptly. The maintenance and testing procedures should be performed in accordance with the manufacturer's recommendations and applicable electrical codes and standards. It is important to keep accurate records of all maintenance and testing activities. These records can be used to track the performance of the automatic transfer switch and to identify any potential problems. The records should be kept in a safe and accessible location. In addition to the automatic transfer switch, the emergency power system should also include a generator. The generator should be sized to provide sufficient power to operate all of the critical loads in the building, including the elevators. The generator should be equipped with an automatic start-up system that will automatically start the generator when the normal power source fails. The generator should be tested regularly to ensure that it is functioning properly. The generator should be maintained in accordance with the manufacturer's recommendations. The emergency power system should also include a fuel supply for the generator. The fuel supply should be sized to provide enough fuel to operate the generator for the required duration. The fuel supply should be stored in a safe and secure location. The fuel supply should be inspected regularly to ensure that it is in good condition. The emergency power system should also include a transfer switch for the fuel supply. The transfer switch should be used to switch between the main fuel supply and a backup fuel supply in the event that the main fuel supply is depleted. The transfer switch should be tested regularly to ensure that it is functioning properly. The emergency power system should also include a battery system for the generator. The battery system should be sized to provide enough power to start the generator. The battery system should be tested regularly to ensure that it is functioning properly. The battery system should be maintained in accordance with the manufacturer's recommendations. The emergency power system should also include a monitoring system. The monitoring system should be used to monitor the performance of the emergency power system. The monitoring system should be able to detect problems with the automatic transfer switch, the generator, the fuel supply, and the battery system. The monitoring system should be able to alert building personnel to any problems with the emergency power system. The monitoring system should be tested regularly to ensure that it is functioning properly. The emergency power system should be designed and installed in accordance with applicable electrical codes and standards. The emergency power system should be inspected by a qualified electrical inspector. The emergency power system should be certified by a recognized testing laboratory.